You'll notice when you do take a look at Gorski's problems, he's not telling you what method of integration to use on any of the problems. So you have to look at it and decide what method of integration is going to be best to get through the problem. When I look at this, I'm saying, oh, I've got a mixture of algebra and trig. My first line of defense is to hope for a u substitution. If it's going to be a u substitution, then I need the derivative of one part to kind of sort of equal the other part. And the reason I say kind of sort of is it can be off by a number. In this case, the two parts that I'm looking at for a function and its derivative are that 2x squared and the 3x. I'm going to come off to the side. And if I make u equal to 2x squared, then my du, the derivative of this, is 4x dx. I don't have 4x dx. What I have is 3x dx. So I'm going to take the part of this that matches what I have over there, meaning the x and the dx. So that x dx, if I divide both sides here by 4 or multiply by 1/4, I'll have 1/4 du is equal to x dx. It's going to let me rewrite the x and the dx part. This, once I replace 2x squared with u, it's going to become sine of u. That x dx again is becoming 1/4 du. We haven't done anything with the 3, but that's okay. It's just a number. So I've got my 3 and my integration symbol. You could skip writing that step out and instead jump straight to our more simplified thing to look at, which would be to take that 3 and the 1/4 to pull all the way out in front of the integral. You don't have to. It's just something that can help kind of visually declutter the integral. Now I look at that and say, who's the function whose derivative is sine of u? And that function whose derivative is sine is negative cosine. So I'm going to have negative 3/4 cosine of u plus a constant. To make sure that I get all of my points, I'm going to look back to the original problem and say we did not have limits of integration. So this was not a definite integral. It's an indefinite integral, which means I need my final answer to be reported back in terms of x. So my final answer is going to be negative 3/4 cosine of 2x squared plus c. I made one change, and now I'm looking at the integral of 3x times sine of 2x dx. Starting off the same way that I do any of these integration problems, I have a mixture of algebra and trig, so I'm checking for the u substitution. It's going to be a u substitution if the derivative of one part is equal to another part of the problem. Well, the derivative of 2x is 2. So it wouldn't take care of that x out in front. And the derivative of 3x is 3. So it wouldn't really do anything for me for what's inside. If it's not a u substitution, especially in the context of this midterm, if it's not a u substitution, I'm thinking about integration by parts. I have a mixture of algebra and trig. I'm going to select which piece to let equal to u by following the rule of late. And I did notice, just from quickly looking through the problems, he does not appear to have any inverse functions in there in the integration. And really his midterm exams in the past have all been pretty straightforward problems. So I'm not going to worry about putting an I in this and either making it Liotte or I late. We're just going to stick with late because I think that's all we're going to need for Gorski. Since this is a mixture of algebra and trig, algebra, or the A part, comes first in the word late. I'm going to set u equal to my algebra part, the 3x. That means that everything else in the problem must be dv. So dv is going to be sine of 2x dx. I'm going to integrate I'm going to take the derivative of u to get du, which will be 3dx. And I need to integrate dv to get v back, meaning I need to find the antiderivative of sine of 2x. If you haven't spent time memorizing those antiderivatives on page 345 yet, we definitely want to, because anytime we just have a number in there, it's good if we can go straight to the antiderivative without spending more time than we need to. So here, the function whose derivative is positive sine is negative cosine. And I'm looking at negative cosine of 2x all over 2. And that dividing by 2 part, that's me sort of undoing the chain rule because of the 2x inside of the trig. I'm going to glue all of that together with my ultraviolet voodoo formula. It's not mine. I just call it ultraviolet voodoo. That part might be mine, not sure. Question in there about what page. The page with the antiderivatives is 345 in my version of the textbook. Back to this. When I put everything together into our ultraviolet voodoo formula, I've got u times v, so 3x times, then we're going to take that negative and the 2 in the denominator and call that negative 1/2 cosine 2x minus the integral of v du. So negative 1/2 cosine 2x times 3 dx. Whenever I'm personally doing integration by parts, before I try to find an antiderivative, I want to clean all of the numbers up, distribute minus signs through, whatever I can do to make it as simplified as possible. Mostly that's so that it's less visually distracting for me. Here, that negative 1/2 I can combine with a 3 to make that negative 3/2 x cosine 2x. Here, I've got a minus, so I'll make that plus. And then the numbers that I'm allowed to pull out in front, I can never change what's inside of the argument of the trig function. So this 2x piece, that belongs with the cosine, and I can't separate that. But the 3 is just being multiplied. So that 3 and the 1/2, I can pull out in front of the integral. And then I'll have cosine of 2x dx. Now that I'm on this step, thinking about that cosine of 2x and going, whose derivative is equal to cosine of something? Well, the derivative of sine is cosine. So this, when I get that antiderivative, we'll have that 3/2. This will turn into sine of 2x over 2. And again, I'm undoing that chain rule piece. We still have the negative 3/2 x cosine 2x out in front and plus a constant. I'm quickly just going to go through the whole dang thing. Why not? Maybe with an example of each thing. So the very first line in that table of indefinite integrals is not super exciting. And it says, if we integrate f of x plus g of x, that's the same thing as separately integrating f of x plus integrating g of x. Well, what that looks like as a problem, right, as an actual integration question, if this said, find the integral of 3x squared plus 10x to the 4th dx, I don't have to come up with some kind of rule that's doing all of it at once, because we've got addition right there, we can break this apart and think about it as two separate pieces, meaning find the antiderivative of 3x squared and add that to the antiderivative of 10x to the fourth. Which leads me to the next piece of this, which is as a formula that looks way worse than it is to use, the integral of x to the n dx is equal to x to the n plus 1 over n plus 1 plus c. That is way more complicated, in my opinion, than remembering what we do in words. So in words, if I have a number times x raised to a power, when I find the antiderivative, I add 1 to the exponent and divide by the new exponent. I have a number times x raised to a power, so I add 1 to the exponent and divide by the new exponent. And then we do want to remember that anytime we're working with indefinite integrals, meaning we do not have limits of integration, we're going to add that plus a constant to the end. There is another rule that is written out on this page that I'm not convinced needed to be written out, but it is something that I've been using a lot. And that's this rule that if we write it out, it looks like a constant times the function, when we integrate that, is equal to the constant times the integral of the function. So just remember that if we have a constant that's being multiplied by a function, we can pull that constant out in front of the integral. It's always our choice. We don't have to, but it's a choice that we can make. So for example, if I go back here to that 3x squared, we could make the choice to move that 3 out in front. And it won't change our final answer because we would still end up with 3 times x, add 1 to the exponent, divide by the new exponent. Okay, now we get into the more fun ones in terms of antiderivatives. This next one is one that we've definitely talked about. We have the integral of e to the x dx. Notation-wise, that integral symbol and the dx together are saying whose function has a derivative of e to the x. Well, the function is e to the x. So I'm going to get e to the x plus c. But this is not what I think you should memorize. I think you should memorize the very next thing in the chart, which looks like the integral of e to the kx dx is equal to 1 over k e to the kx plus c. Now, this is really something that I've been exploiting all the time, that if we have an integral and there's a number sitting next to the x somewhere, like it's a constant times x, not a constant times x to a power, just a constant times x, then when we find the antiderivative, we're sort of undoing that chain rule by dividing by the constant. So for example, if I had e to the 5x dx, this integration rule means we get 1/5 e to the 5x plus c. What I don't understand in the chart, so they do this for e to the x, but then they totally miss the opportunity to do it with our other functions as well. Here's what I mean by that. The chart lists an integral of 1 over x dx as, again, whose derivative is that? Natural log. So ln absolute value of x plus c. But what I wish they had put into the chart is that the integral of 1 over ax plus b is equal to 1 over a times natural log of ax plus b, where a and b are constants. So they do it for e to the x generically, but they don't write it out for natural log of x generically. But I think this is one that's worth putting in your toolkit. And there's a question about, does it matter if you write it as a 1/5 or as divided by 5? Not at all. This is absolutely equivalent to saying e to the 5x divided by 5. However, it works better in your head. Okay. And an example for the natural log one, absolutely. And I'm going to do this in reverse first, and then we'll do an integral. But I'm going to zoom back to 17a for a second. So if my function was natural log of, how about 3x plus 7, and I had to take the derivative, well, dy dx, derivative of natural log of something is 1 over the something times, chain rule says I have to take the derivative of the inside, and the derivative of the inside in this case is 3. So it would be times 3. Whenever we're doing this thing where we're sort of adjusting by that constant because of the chain rule, when we were taking derivatives, we would end up multiplying by that constant. And now that we're doing antiderivatives, we're going to end up dividing by that constant. Suppose I started with 1 over 2x plus 5, then that antiderivative is going to be natural log of absolute value of 2x plus 5 divided by 2. Or, plus a constant. Or we can also write that as 1/2 ln absolute value of 2x plus 5 plus a constant. When we were taking derivatives, we're multiplying by that for the chain rule. When we're taking these antiderivatives, we're going to divide by it. Now, we want to be really careful. This only works when it's just a number. If it's anything more complicated inside of here than like a linear term, then we probably want to be thinking about a use substitution or integration by parts. I'm going to move on to the next one in the chart. So the next one in the chart here is the integral of a to the x dx. And if we're going to, and our antiderivative here is a to the x divided by natural log of a plus a constant. This isn't quite that same rule where we're dividing by the number, but this is coming from remembering some facts about our derivative rules. So if y is equal to a to the x, then when we take the derivative and get our dy dx going, this derivative was a to the x times natural log of a. And just kind of as a general thing to help you remember it, if we were going to multiply by a number when we took the derivative, then when we take the antiderivative, we're usually dividing by that number. And page 345 does not have the derivatives on it. It only has antiderivatives. I'm just showing you those for fun. The next 6 that are in here are all trig functions. So as a quick trig review for us, let's do our 17a, take a bunch of trig derivatives. Let's do derivative of sine, derivative of cosine, derivative of tangent. What else is on here? Okay, everybody's on here. Derivative of cosecant, derivative of secant, and derivative of cotangent. And I will say, being super good with derivatives, that's what's going to help with recognizing those U substitutions. Okay. Quick rundown. Derivative of sine of x, cosine of x. Derivative of cosine of x, negative sine of x. Derivative of tangent of x, secant squared x. Derivative of cosecant of x, negative cosecant x, cotangent x. Derivative of secant of x, secant of x, tangent of x. Derivative of cotangent of x, negative cosecant squared x. So on page 345, each of these are written in reverse in terms of their antiderivative. So this first one is written as the integral of sine of x dx is equal to negative cosine x plus c. The integral of cosine of x dx is equal to sine of x plus c. The integral of secant squared x dx is tangent of x plus c. The integral of, and some of these, they've switched around the signs in the chart, but the integral of cosecant x cotangent x dx is negative cosecant of x plus c. The integral of secant x tangent x dx is secant of x plus c. And the integral of cosecant squared x dx is negative cotangent of x plus c. So if you have these derivatives memorized, you already have the antiderivatives memorized. They're just all asked backwards. Now I'm going to point out that in this list, I think there's somebody missing. So this list gives us what the antiderivative of sine is and what the antiderivative of cosine is, but this list didn't tell us what the integral of tangent is. So let's figure out what the integral of tangent is so we can add it to our list. I'm going to erase my derivatives. So if I gave you the integral of tangent of x to do, it's not something nice in our list of antiderivatives. So we're going to have to try something else. There's only one thing. So integration by parts doesn't really seem like a good choice. So I'm wondering if there's some way we can rewrite it. And that's by using the fact that tangent of x is actually sine of x divided by cosine of x. Now I have two pieces. So now I'm thinking to myself, hey, does the derivative of one part equal the other part? Why, yes, it does. In fact, The derivative of sine is cosine, and the derivative of cosine is negative sine, so this could kind of go either way. As a general statement, if you're not sure which part to choose to let equal to u, try the bottom. If u is equal to cosine of x, then the derivative of cosine is negative sine of x, which I almost have, I just don't have that minus sign, which means that I can rewrite this, swapping out the sine of x dx for a negative du, or I can put my negative out in front, du, and cosine becomes u. Now I can think about whose derivative is equal to 1 over u. Well, that's natural log. So I'm looking at natural log absolute value of u plus a constant. But the question was asked to us in terms of x's. So let's answer it in terms of x's. And now I'm looking at negative natural log of cosine x plus c. Sometimes, if you're looking at integration tables, they don't list it this way for the antiderivative of tangent because they use log rules and trig rules to rewrite this. And in section 5.7, there are problems in there that are asking you to like use a table and then plug it into an integral calculator and see if you get the same thing. And when you don't get the same thing, do the work to make them look the same. So here, doing the work to make things look the same would be noting that that negative 1 in front of the ln can come inside as an exponent to turn that into natural log of cosine of x to the negative 1 power. But that's the same as 1 over cosine, and 1 over cosine is the same as secant. So a lot of times, the way this integral is written in a table is that the integral of tangent of x dx is equal to natural log absolute value of secant of x plus a constant. Now I will say, this one is not in that table on 345. I would be a little bit cautious about just jumping right here with an answer on your exam. I probably would show a u substitution if you were asked about tangent of x, really just because you're not in a proctored testing environment, so most instructors at this point are kind of extra cautious about thinking that people may have cheated. If you find this somewhere in the textbook, it is in the textbook, so that you can say, hey, I memorized this from page blah, 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 then you're good to go. Okay. There is one last one on that page of antiderivatives. And that is the integral of 1 over x squared plus 1. And this, we are supposed to remember from 17a, hey, that's the derivative of arctangent, or tan inverse. Okay. Well, if we're going to find all functions, f of t, that satisfy this, we have been given a derivative, which means we're going to have to find the antiderivative in order to get that f of t by itself. So it didn't ask us to do an integral, but I know that we need to. So f of t is going to be the integral of 1 over the cube root of t plus 6 dt. Looking at this, I have something that looks like a t raised to a power. It's just not written in the most convenient form. So if I'm going to apply that power rule where I add 1 to the exponent, divide by the new exponent, I first need to rewrite this question. And I'm going to rewrite that to look like t to the negative 1/3 power plus 6. Now I can find that antiderivative. I can add 1 to the exponent. So negative 1/3 plus 1 is going to give me positive 2/3. So I'll have t to the 2/3. Okay, I'm regretting my choice over here, but that's what I get for trying to do it in my head. And then I'm going to divide by the 2/3. And that 6 is going to become 6t, but the whole thing will be plus a constant. So that's generically my function f of t. But we have more information than that. We have been given an initial condition, which is enough to let us solve for the value of c. So I'm going to take this initial condition and say, okay, when I plug in 1 for t, then my f of t is supposed to be 8/3. So 8/3 should be equal to 1. Well, 1 raised to the 2/3 is still 1. So 1 divided by 2/3 plus 6 times 1 plus a constant. I'm going to rewrite this. So I've got 8/3 is equal to, when I flip that over, 3/2 plus 6 plus c. Now, option 1, I could just solve for c by subtracting these two to the other side and not simplifying any of it out. If I did want to simplify it out, then personally, I would multiply everything by 6 to eliminate all of the fractions. So if I multiply this side by 6 and this side by 6, over here, the 6/3 would leave me with 2. 2 times 8 is 16. When I distribute the 6 in here, 6/2 is going to give me a 3. 3 times 3, I've got 9. 6 plus 6 is 36. And then I'd have plus 6c. So if I combine all these numbers together, 9 plus 36 is 45. 16 minus 45. Man, it's a Monday afternoon. Some number. Okay, let me do this. Yeah. What did I say? 16 minus 45? It's this kind of Monday. Great. Negative 29 it is equal to 6c. So my constant is equal to negative 29/6. So my final answer is to take that negative 29/6 and plug it in right here. And bam, there's my answer. First of all, oh wait, no, we're not going to do this. You can write it on your paper, but I'm going to make it worse momentarily. If this was the question, I would not do a U substitution. Because if this were the question, I would just distribute the x cubed in. But now I'm going to turn it into something that I would do a U substitution for. Now I'm doing a U substitution all day long because I don't want to have to distribute this out to the 8th power. Bam times bam times bam times 8 times. No, thank you. So I'm going to look at this and say, hey, does the derivative of one part equal the other part? Well, kind of, sort of, almost. If I let all of this be equal to u, then du would be 4x cubed. Now I don't have the 4, but dx. I don't have the 4, but I have the x cubed dx. No worries. 1/4 du becomes x cubed dx. And I can replace the x cubed dx with 1/4 du. Now that 5x to the 4th in parentheses, whole thing to the 8th power, becomes u to the 8th. But I have to be careful and change those limits of integration. When we have a definite integral, whatever variable is out here it is implied that these two are values of x. So now, because I've got a du here, I have to change these bounds to both be in reference to u. So if I come up here, then we've got our x values and our corresponding u values. When x is 0, then when I plug in 0, 0 to the 4th is 0, plus 5 is 5. When I plug in 2, 2 to the 4th is 16, and 16 plus 5 is 21. So when we write our u substitution, our limits of integration should now go from 5 to 21. Now I'm going to find that antiderivative, add 1 to the exponent, divide by the new exponent. So my 1/4 is coming along for the ride. I'll have u to the 9th divided by 9. I don't need plus a constant because it was a definite integral. I'm going to plug in the 5 and the 21. We're going to plug in the top, subtract off plugging in the bottom. 4 times 9 is going to give me 36 in the denominator. So I'm going to have 21 to the 9th over 36 minus 5 to the 9th over 36. And we are just going to quit there because we're not supposed to use a calculator, our notes, the internet, our book, or our friends while we're taking the midterm. Bam, I'm done.